So let's practice finding those distances by applying it in a very IB way. So example number one is a very IB type of problem. A storage box for garden tools in the shape of this cuboid is shown in the diagram. Vertex A has coordinates 2, 3, 4. All coordinates are given in meters, and we're going to determine the following information. So in the real world, when we're trying to decipher or determine solutions to problems, a lot of times when we need to use mathematics, it's nice to be able to represent the situation that's going on in a coordinate plane. And since the world is three-dimensional, it would make sense that we have to have a coordinate plane that is also three-dimensional. So for instance, where we're trying to find the dimensions of a toolbox or a storage box, we might try and assign coordinates for certain parts of that room. And now some of these coordinates, right, like finding the length of RQ, right? Those are things that you probably already know, but maybe you don't know what the diagonal length here is. Maybe you want to know what the angle is between certain things. And all of those are just a little bit more complicated math ideas, and they should be represented in a mathy way in order to be able to use mathematical concepts on them. Representing real-world situations using a coordinate plane is a very good first step for a potential IA. If you wanted to represent the curve of a ball that you've kicked, you would represent it on a coordinate plane before you found the equation of the model. If you wanted to represent the slope going down a ski slope, you would be first putting it on a coordinate plane before you determine what the equation of the model is. So this is a very important first step for a lot of real-world applications. Okay, so what does it mean to have the points 2, 3, 4? Well, remember that our three-dimensional points follow x, y, z. And now notice that our axes here are slightly different than what we see in a two-dimensional way. This guy right here is our x-axis, and then our y-axis, and then our z-axis. This subject is notoriously difficult to visualize. So if you're having a hard time, I would highly recommend checking out something like Desmos or checking out something like GeoGebra, in which they can virtually model, and I'll probably have some sort of activity that we'll do in class together where we'll virtually model a three-dimensional plane and we can kind of see how they all interact together. Since the coordinate here is 2, 3, 4, that means that in order to graph this point, we can follow it. We went 2 of a distance along the x-axis. So we started from 0, how we graph things normally, right? When we're plotting points on an x and y axis, we take our x value and follow that along the x-axis, and then take our y value and then follow that up along the y-axis. So here we've got A, 2 comes out this way, and then 3 follows along the y-axis, and then 4 then is how we plotted that final point. That gives us a lot of information about all of the measurements of all of the sides of this cuboid. If we started at the origin and went out to R at a distance of 2, then I know that this length and this length and this length and this length are all 2. Then if I followed along here to go a distance of 3 before I ended on my final spot here at A, that means that my distance here is 3, which means this is 3 and this is 3 and this is 3. Then my final distance to go up would be a distance of 4, which tells me that this is a height of 4. Using all of that, now we can kind of work backwards and try and find the coordinates of other points. For example, R. R is right here. So in order to travel from the origin to the R, we just moved in one direction. We moved out an x value of 4. Sorry, not 4, 2. But notice we didn't move out along the y-axis at all. We stayed put. We didn't move anywhere along the y-axis. So our y value is 0. And we didn't move up or down at all. So our z value is also 0. Let's try it again. This is complicated. So if you didn't get it the first time, we're just going to keep explaining it. The vertex C here, we start at the origin and we didn't move out along the x-axis at all. Notice that we didn't move here at all before we moved over to C, we just straight moved over here. But that means in order to represent our x movement, we didn't do any of that movement, so it's a 0. Then we moved in a y movement way to C, which we've determined that that distance is 3. And then we didn't move up or down at all, we just stayed there, which means our z value is 0. Okay, hopefully that one made a little bit more sense. If not, we've still got 2 more points to practice this on. Vertex B, we did not move out on the x dimension at all, so our x value is going to be 0. We then were able to move out this distance, so we know in the y direction we moved a distance of 3, because this distance is 3 and this distance is 3. And then we moved up to get us to our final resting place at B. That distance right there is a distance of 4 in the z direction. Last one, Q. Q is moving out in a x movement, right? It's coming out in this way. So it moved out in the x direction, a distance of 2. And then it did not move at all in the y direction. It didn't move this way at all. So we know that our y value is going to be 0. But then we do know that we moved in a z direction. We moved up at that distance of 4. All right. We want to find the maximum length of a garden tool that can fit in this storage box. The maximum length that we're going to be able to fit in this storage box is going to be the diagonal here, which is something that you hopefully makes sense. If you're trying to fit something in a box and it doesn't fit one way and it doesn't fit the other way, you tend to try the diagonal to see if it'll work that way. So this is the longest distance that you can put in a solid way in a box shape. So the largest garden tool that we can fit in the storage box is going to be that distance, the distance of RB. Thankfully, we have the coordinates of both R and B. We found them up here. IB is really great about that you almost always use the previous problem in order to solve the next one. They're giving you little hints of like, okay, this is kind of how you would solve it. So since it's a 3-dimensional coordinate plane, in order to find the distance, I need to use my 3-dimensional distance formula, which is really just, hey, find the distance of your x values and then square it. Find the distance between your y values, square it, and then find the distance between your z values and square it. I would like for you to go ahead and tell me what that is to 3 significant figures. You should have gotten the square root of 29. If not, go back and double check your calculations. 3 significant figures means that that answer is 5.39, and it does say that our measurements are given to us in meters. So I do know that that's 5.39 meters. Okay. Problem C is pretty straightforward, but it's a hint for problem D of what you're supposed to use. So it says find the height RQ of the storage box, and we've already found the height. In order to know what that coordinate of Q is, we would have had to know that going up to Q was a distance of 4. So we do know that RQ is 4. Now it says find the angle between BQ and BR. Here is BQ. I'll do it in a different color. If you have a highlighter, this might be a good time to or a different colored pen. If you're a visual person, which I think a lot of you are. So we want to find the angle between those two. And finding angles, always, we need to find a way to triangulate it. We need to make a triangle here in order to use trigonometry in order to solve for these missing angles. Well, in order to complete it, we have QR right here. Which, hey, didn't we just talk about finding that information for QR? We know that these guys are a right angle, which means we found a right triangle. If I want to draw it, doesn't have to be the best drawing, but I know that that is 4. This is R, this is Q, and this is B. Whoops, sorry. So we know that QR is 4. We've also solved for BR, or RB. I'm going to leave it as the square root of 29. We would like to solve for this angle right here. I'm going to label it as theta, like we tend to do when we're solving for angles. So in order to solve for this angle right here, I need to reference back to trigonometry. Which type of trigonometry will I be using? Hopefully you said SOHCAHTOA, which is our right triangle trigonometry. Since it's a right triangle, we can use Pythagorean theorem or SOHCAHTOA. And since we're not trying to solve for the missing side length, we're trying to solve for an angle, we're going to be using SOHCAHTOA. You can even write it out. SOHCAHTOA. Remember, you can label the side lengths, right? 4 is opposite of the angle because it's like a spotlight going over there. This guy is opposite of the 90 degrees, so it's a hypotenuse. So since we have the opposite and the hypotenuse, we're going to be using sine. Sine of theta is equal to 4 over the square root of 29. In order to solve for this, you can use your numerical solve, or you can use your inverse trig, right? That's sine to the -1 of 4 over the square root of 29, and that gives you theta. Go ahead and solve for that to 3 significant figures. This one was tricky to put into 3 significant figures. You should have gotten like 47.96 or something like that. So 3 significant figures. It was like 47.96 ... We know that this is our third significant figure, first, second, third significant figure. Looking at this guy means it rounds up. So it rounds to 48. To make it 3 sig figs, you put 0.0, saying, yes, I rounded it to 3 sig figs, and it rounded up to 48.0. Which is just slightly different than just writing 48, which might imply that you only rounded to 2 significant figures. Okay, so there's a little bit of a real-world application of why finding the distance might be important and labeling real-world situations in a coordinate way.